So, excellent. So, good morning, good afternoon, and good night to everyone, depending on where you are. It is my pleasure to actually be able to introduce to you today's speaker. We are going to have a talk by Dr. Da Silva. Dr. Da Silva is currently a research scientist at the Center for Accelerator Science at Old Dominion University in Virginia in the US since 2014. She got her bachelor's from engineering physics and information technology from the University of Colombo in Sri Lanka in 2004. She got her master in physics at ODU as well in 2008, and her PhD in accelerator physics in 2014 from ODU as well. So Dr. Da Silva has worked in many SRF projects that include, but are not limited to, spoke cavities, transverse deflectors, dual axis cavities for energy recovery linacs, and more. Perhaps one of the most significant is the crab cavities for the high luminosity upgrade of the LHC, where her design is currently under series production to be installed in the machine in the near future. So it's really a pleasure for me, particularly to invite Suba to start sharing with us her seminar for today. Please, Suba.
Thanks, Alex. Okay, so good morning, everybody, and good afternoon, wherever you guys are. Thank you, Sal, for inviting me to give this seminar for all of you guys. So today I picked the topic to talk about non-elliptical cavities. I wish there had been an elliptical cavities seminar before, but I missed it. So, but we can probably do one later and connect all of together. So in here, I'm going to show interesting cavity shapes. Most of you may have seen most of those cavity shapes in different particle accelerators throughout the world. So here's the outline. I will show some of the cavity geometries that's out there in the world at the moment, and why we need these kind of strange interesting shaped cavities for particle accelerators. Then I will try to cover two aspects of it, where these types of cavities are used for particle acceleration, and as well as to deflect and crab particle beams. So to begin with, let's quickly have a look at the elliptical cavities. So pretty much everybody is familiar with these elliptical cavities. You see them in single cell shaped or in multi-cell, maybe 3-cell, 5-cell, 7, 9, and so on. And these cavities you see in superconducting cavities made out of niobium or copper cavities. So you can see some of the examples here. This is the Ciencia cavity at Cornell, which is a copper at 500 megahertz. It's a big cavity. You can see the size, and you can see some of the other cavities on the table, which are much smaller. And this is the LEP cavity, which is a niobium coated on copper. This is LEP at CERN at 350 megahertz. And then this is the CBEF cavity. The 5-cell at 1500 megahertz. This is one of the very first superconducting cavities that was built for particle accelerators. And then below here is a 1300 9-cell cavity, and this frequency and this cavity is actually very much used in many applications in DAISY, LCLS2, and so on. So now moving from the elliptical cavities, here I'm showing examples of non-elliptical cavities which are used for particle acceleration. So unlike in the elliptical cavities where you see copper cavities, I'm focusing on superconducting cavities. So these are all niobium cavities. And the first one is a quarter wave cavity. So the length is at a quarter wavelength. And this is the world's first half-wave cavity. And you have the split a ring resonator. It's still used in argon in their APS machine, but it's not commonly built anymore. And then you can have superconducting RF2 cavities. These are the single spoke cavities. In the spoke cavities, you can even have multi-spoke. And then finally, something called twin axis cavity. So I will go through most of these cavity geometries and explain their properties and their advantages and how we can use them in particle accelerators. Then coming on to these interesting shapes where we use them to deflect or grab particle beams. So it's not to give energy to the beam, but to deflect or bend the beam or grab the beam. So I will explain later what these applications mean. And here, the first one is put down is a squashed elliptical cavity. So this is similar to an elliptical cavity, but it's elongated in one direction. And then you have four-rod cavity. This is from UK. And then you have TE type cavities, which is called the double quarter wave and RF dipole. So I will try to go through as many of these cavities as possible. So let's first look at why we need these non-elliptical cavities. So the electrons or the electron linacs are, the cavities are designed at beta equals 1 because the mass is so small that the time it takes to get to beta 1 is so small. So you don't need any non-elliptical cavities. But when we are accelerating protons or heavy ions, the mass is about almost 2,000 times more than electrons. So you do need cavities that can operate at beta less than 1. Beta meaning the V over C. V is the velocity of the particle and C is the speed of light. So you need to design cavities such that you can have variety of beta acceleration in the machine. So why we cannot use elliptical cavities still at low betas is there are several reasons. Here listed few are you always tend to have mechanical problems. Their mechanical rigidity is not good. And then you have multipacting issues. And even you cannot get good RF efficiency. So it's quite limited at very low betas to use elliptical cavities. You still can use elliptical cavities at a certain beta, maybe above like beta 0.5 or 0.6, but it's not at all favorable for very low betas. So the only solution is to use TEM type cavities. Here, this is an example that shows with an ion source, you have, before you get the superconducting linac with high beta, you need other shapes to accelerate up until that point. It can be RFQ, a drift tube, or it can be a so this is for these are normal conducting, but for a superconducting machine, it can be a half wave, quarter wave cavities, spoke cavities, and combination of those. So let's look at the spectrum of the velocity of the particles as a function of the frequency. So as we said, we need these kind of cavities to accelerate protons or heavy ions with varying beta. So for very small beta, the preferable cavity shape is a quarter wave cavity, and they operate at much lower frequency, most of them 100 or below megahertz. And then the next region of beta from 0.1 to up until even 0.5, you can use half wave cavities. And they are around 100 to maybe 300 megahertz, that range of frequency. And then you have half wave cavity moving on to spoke cavities, or they can be single spoke or multi-spoke at beta close to 0.5. So beyond beta 0.5, you can use elliptical cavities as shown here. You can still have varying beta, but still efficiently accelerate the particles with elliptical cavities for beta above 0.5. Recently, there had been research going on to use these TEM type cavities even at very high beta. So shown here is this big cavity is a 325 megahertz beta 0.82 cavity. It's a single spoke cavity. And then there's a multiple spoke, which is a two spoke cavity. This is a beta 1 cavity at 500 megahertz. And these are proposed for very compact, small machines, which I will come to a little later. So looking at the limitations of using elliptical cavities, let's see why it's not effective at very low beta. So with varying beta, as I explained, so you have elliptical cavities and in CW applications, mostly from beta above 0.5, and for pulse machines, even above 0.6. So if you take a multi-cell elliptical cavity, we know that single cell length is about a lambda half. So with varying beta, it will be beta lambda half. And then the cavity diameter is roughly in the order of lambda. So if you take the ratio of the cavity length to diameter is in the order of half beta. So now if you go to very low beta, it's very narrow, as you can see here. And then as you increase the beta, you can get wider cell. So at very low betas, it's more like a bellow. So it's not at all favorable because of the poor mechanical stability, and you do not get good RF efficiency, and also strong multiplexing at the equator region that you cannot eliminate. So, and then around beta 0.5, it will work in CW, but not much in the pulse. But then above the high beta ones, the elliptical cavities are there in operation at the moment, like in SNS. The other need of non-elliptical cavity is where we need to deflect or crab the beam. So here what we need is to create a transverse kick to the beam. So with the non-elliptical accelerating cavities, what you do is create a longitudinal electric field in the cavity so that you can transfer energy to the beam. Here what we do is we create a transverse electric field and such that it will kick the beam. So depending on the location where you kick the beam, it can be either deflecting cavity or a crabbing cavity. So you cannot do that with simple elliptical cavities because the elliptical cavities operate in a TM010 mode with a longitudinal electric field. So that's why you need to design cavities with different field profiles. So that's why it is not an elliptical shaped cavity or operating in a TM010. I'll later show different types of cavities where we use TE11 or TM11 or TEM type deflecting and crabbing cavities. Let's quickly look at the applications. I'm not going detail into the application types, but you can find many literature based on different machines out there in the world to read and understand more on these applications. But I have summarized here a somewhat list of different types of applications where we can use these non-elliptical cavities. One of them is Linux for nuclear physics research, and this is usually the beta range in 0.2 to 0.5, where you accelerate light and heavy ions, and in CW operation for currents around 1 microamp. Then these cavities are also used as the drivers for radioactive ion beams and accelerator driven systems, with again betas around 0.3 to 0.9. And in CW operation. These cavities are also used for radioisotope production, and then for neutron spallation sources like the SNS in Oak Ridge, and then for accelerators for material irradiation, and then compact high beta Linux. These are proposed machines, but we don't have built machines as of yet. but these are ideal for very compact small machines. Again, but these we are talking about beta equals 1. And then the final is the deflecting and crabbing, where again the beta is 1, where you can deflect or crab either electrons or protons or even heavy ions. So here is a kind of world map of different accelerator facilities throughout the world that does research on non-elliptical cavities. So you can check out those machines and research if you like to follow on more on this area. So coming to learning about the details of these type of cavities. So we know they either operate in TM type or TE type or TEM type. So this is like the full electromagnetic profile of cavities that you can use for these kind of cavities. The simplest form to look into understanding these field profiles is to look into a pillbox cavity. So for a pillbox cavity, you can even do it analytically and do the TM modes and TE modes as shown here, and you can try to get an understanding of different mode profiles. So you can categorize them based on a pillbox cavity and try to get a better understanding. So the TM010 is the mode used for accelerating for elliptical cavities. It has a purely longitudinal electric field that transfers energy to the beam in accelerating the particle. And these electric and magnetic fields have no angular dependence. So this is, as I said, is the mode of the preference in elliptical cavities. But then going one step further, you have TM0NP, where it's still a monopole mode with a longitudinal electric field, but that electric field is not on axis. So you can use a higher order of a TM mode, and those can be used in applications in such as the twin-axis cavity, which I'll show later. Then if we go TM1NP or 110, for example, this is a Scotched elliptical cavity, and this introduced, the moment you have the 1 here, it becomes a dipole mode, and then this can be used to deflect the beam as a deflecting or a crabbing. And then the TE mode, where you don't have a longitudinal TE field, so it will have a transverse electric field in the cavity, and it does not couple to the beam on axis, so it's not for crabbing. And then you have the EM mode type cavities, where it's a coaxial geometry, so you need an inner conductor and an outer conductor. And these type of cavities you can use for particle acceleration as well as for both deflecting and crabbing. So we'll go through them in detail later. So similar to the pillbox cavity, you can do the electromagnetic field profile for a coaxial. So you will have an inner conductor with radius A and an outer conductor with a radius B, and where they are terminated with ground plates or end plates as shown here. And then you will have a electrical field, which is radial, given by this, and then a circulating magnetic field. So you can see how we can use this kind of profile for particle acceleration. So let's quickly look at some of those cavity shapes and categorize them with the field profile. So we talked about TM type cavity, where there's longitudinal electric field on axis. So this is the twin axis cavity, but operates in a TM110 mode. And you have 2 beam pipes, where you have the two electric fields separated with this gap, and then you use it for accelerating multiple beams at the same time. And then you have the Scotched elliptical, which again operates in a TM110 mode, but here what we are doing is not using the electric field that's at these ends of the cavity, but uses the magnetic field to give a kick to the beam. So you can use the same electromagnetic field profile, but where you place the beam makes a difference in the application. Then you have TE type cavities, which operates in TE21, which we call a RF quadrupole that we use for very low beta particle acceleration. And again, TE11 like modes that where you use a transverse electric field to deflect or crab the beam. And then you have many TEM type cavities that are used for particle acceleration. These are the most popular cavities, the quarter wave, half wave, and the spoke cavities. And then you also have TEM type four-rod cavity, which is used for deflecting and crabbing. So as you can see, there is a whole variety of cavity geometries, and you can be more innovative and think free and come up with many interesting shapes that works for particle acceleration or even deflecting and crabbing beams. So since you have many degrees of freedom and many parameters that you can optimize in a cavity compared to simple elliptical cavity, it can lead to complicated designs if you try to overestimate it. But as I want to kind of emphasize, it is more fun to kind of play with these kind of geometries where you can optimize it with many parameters and come up with many designs that suits a particular application. So there's no one design for one fixed half wave design or one fixed quarter wave design or one fixed spoke design. So it's all depends on the application, and these many parameters allows you to optimize it based on the application. So as you have seen these cavity shapes, these are pure 3D geometries. So you cannot use simple 2D codes. To a certain extent, you can do them analytically, but once you have all the features such as curving of these edges and beam pipes, you no longer can do a complete cavity geometry using a 2D codes. So you do need 3D codes, and there's many codes out there. Some of them are commercially available to many accelerator facilities where you can use them. And you can check out this tutorial talk where they talk about these all these packages to use in optimizing cavity geometries. So let's quickly look at the basic principles of these cavities, specifically in using these cavities for particle acceleration. So as you have so far noticed, you need a particular gap in acceleration. So you have electric field between these two gaps. It's a standing wave, and that's what that creates or transfers the energy to the beam. So you can write the time-dependent electric field as a function of the electric field between the gap and the time dependence of it, including phi, which is a constant, but it defines the RF phase in which where the particle is with respect to the RF field. So for on crest of acceleration, you would want the phi to be 0, so such that the particle is at the center of the cavity. It is in a line with the phase. And then you can calculate the accelerating voltage, or we call the effective voltage, or the VC, or the cavity voltage, by integrating it throughout the gap, and that's what gives you the cavity voltage. So this is simple definition of getting the cavity voltage, and then you can convert it to gradient, because most of the accelerating field, we define them as gradients and not much as voltages. So that's also because it's length dependent. So that's why we define it as gradient with units of megavolts per meter. So it's normalized to the length, and then you can multiply by the length and know how much is the effective voltage, the total effective voltage. So this shows detailed steps in getting into the final formula. So with varying beta, we know that the time and position are linked to the velocity. So we have this beta term in here. And then in here, we also have the phase term to tie it to the time. And when you do the expansion, these are the terms that you have. And if you think of a simple gap, though it shows two gaps here, but if you think of a simple gap, it's in the cosine form. So you can drop the sine term, and then this gives you the effective cavity voltage. And this VC is defined without the phase, but it'll be the total voltage will be VC times cosine phi. So if it's on crest, this term will be 1. So as I said, what you define is the accelerating gradient, and you define it such a way which is called the EA divided by the length. So the length is the total length. Sometimes they do the total length, or sometimes they do as a multiplication of how many half beta lambdas. So usually a gap is a beta lambda half, and how many gaps you have is what defines the total length. And it's always very important in these type of cavities to define what the length is, so that you can accurately calculate the total voltage. The next term is to see how much is the energy gain, so that it's simply the same integral multiplied with the charge of the particle. And unlike the standard elliptical cavities where you operate at beta equals 1, here we define two additional parameters. One is the transit time factor. This gives the time variation of the field during the particle transit through the gap. So it defines as it goes through a certain gap, the variation of the time. And the second term is called the velocity acceptance. So this gives within that gap how effective is, because when you design a cavity, a quarter wave, half wave, or even a spoke cavity, you have to define each cavity to a particular beta, because you cannot, the moment you set the gap, the cavity has a fixed beta, but you know the particle velocity is varying. So this gives you how much is the cavity is effective in that varying beta range for the gap that you have defined. So we'll come to a little later to look at a little bit more on the velocity acceptance. So let's quickly look at a single gap structure, and then I will later show a two gap, and then you can use those to do multiple gaps and determine whether you need to do a single gap cavity or a multiple gap cavity, or then how many gaps you would want in a particular design. So here I have a single gap with a aperture radius of B, and the gap is defined as G. So you can calculate the voltage by integrating the field in between the gap. So for simplest form, we use it as a square one, but it's more of a cosine in practical, because the field decay into the aperture outside the gap. But for now, for simplicity, let's use it as a square profile. And then once you integrate that with between the gap, you get this term for VC. And then from the previous definition of the transit time factor, you can calculate the transit time factor formula for a single gap. So this is the formula for a single gap. It has the sign dependence as a function of the gap, and then the beta. And here you the plot shows a for a single gap with two apertures of 15 millimeter and 30 millimeter for a 350 megahertz cavity, and with a gap of 30 millimeters. So you can see as the aperture changes, the transit time factor variation changes. So the actual effective gap is not completely dependent on this gap width, but also has an effect of the aperture radius or the diameter. So, so you want to make it effective in uh, transferring the energy. So you want the radius or the diameter to be less than the gap for this to be effective. And then the other rule of thumb is that, so that defines the limitation on the aperture compared to the gap. But now, how do we know what is the effective gap? So the effective gap is always has to be less than beta lambda half. So this gives you a effective transit time factor of about 0.63 for this particular gap size. Then when you go into two gaps, so you have two gaps with alternating electric field between the two gaps. And then again, going into the square profile, so this it will be more of a sinusoidal than a cosine. So you can, similar to that you did for one gap, you can integrate the field for the full cavity, including both the gaps from here to here. And now the transit time factor has two terms. The first term is coming from one gap term, and this second sign term is from the second gap. So when you have multiple gaps, only the second term changes. So this first term is fixed, but it can be sine squared for the three gap. So if you look at the plot, the red one shows one gap for one gap, and the moment you have a second gap, it throws off, and the more gaps you have, the range narrows. So this is where the accepted voltage range comes into play. So this is a simple nomenclature before I go into explaining the voltage acceptance. For general purposes, we define a normalized transit time factor for, so the gap will have a fixed beta designed, and then we normalize it to that. And it does not change the energy gain, but it alters the definition slightly. But it's somewhat mathematical, but does not affect the performance of the cavity. So going by that definitions, when you have multiple gaps, so if it's a single gap, it's at 1 as throughout the beta. And then the more gaps you have, the narrower the region is. So this is what we define as the velocity acceptance. So if you have a two gap, you have a much wider range of acceptable velocities that you can accelerate using that particular gap. But then the more gaps you have, your particle velocity needs to be within this region for it to be effectively accelerated. So the larger the gap, you can, the constant beta calls, if you want a constant beta, what you want is a large n, but we know at very low betas, the beta can vary very fast. So then what you need is very small n. So you don't want to put multiple gaps at very low betas, like less than 0.1 or less than 0.2, but you can consider having multiple gaps at 0.5. So similar to multi-cell elliptical cavities, where you have many cells at betas around 0.5, 0.6. So then you can use all these definitions to define the cavity parameters. I'm not going to go into detail. I put down a reference so you can calculate these for these cavities. So once you know the effective voltage, you can pretty much calculate all the cavity parameters. So these are the important parameters where it determines the performance of the cavity and the applicability cavity for a particular application. So you can check it out, but it's worth going through it to fully understand. So the knowledge that you have here, or the knowledge that you have in calculating the particular voltage or the transit time factors, how you can incorporate it to getting ultimate cavity parameters. So let's now look into types of accelerating cavities. I think I have to quickly move on. So here I'm talking primarily about TEM type cavities. So as I said, we have quarter waves, half waves, and spoke cavities. And let's look into these one by one and see their RF properties. So quarter wave resonators is called quarter wave because you have an inner conductor and an outer conductor, but the inner conductor is of lambda, quarter lambda. And you have strong electric field at the end or the tip of the probe, and then you have the top of the cavity. So here you what you do is you open up you put a hole through it or put a beam tube in the inner conductor so such that you can get particles through. And here in the quarter wave, as you see, there is a electric field between the gap in this direction as well. So this limits the performance in particularly quarter wave cavity. So what you do is you optimize the tip in such a way that you can get higher acceleration in this direction, but try to reduce this one. But at certain point, as you increase in frequency, it's no longer effective. So you cannot use this kind of cavities at much higher frequencies. So I have listed these formulas, but I'm not going to go through these, but you can always calculate them analytically, and if you are interested. And I have listed the further these parameters where you can get all the cavity parameters, and you can see the geometrical fact and is as a function of beta. So you get a feeling for what kind of beta, what kind of geometric factor, and what kind of energy content you will have. So it's always good to have these analytical formulas, even if it's not the closer to the ideal shape, but it gives you an idea whether you are going in the right direction in optimizing the cavity. So you can always analytically solve these and get these expressions. So let's look into the half wave cavity. So half wave cavity is like two coaxial cavities put next to each other, and where the inner conductor is connected. So the length will be lambda half, and then you have a beam pipe put through at the middle, and then you have the strong electric field between the gaps where you use it for particle acceleration. So the power in a half wave cavity is twice the quarter wave cavity. And then you have the magnetic field on the top and the bottom of the cavity that circulates around the cavity. So similar to the quarter wave cavity, I have put down all the formulas again, but I'm not going to go through them, but you're welcome to have a look at it later. So let's move on to the quarter wave cavity. So the quarter wave cavity, comparing the quarter wave cavity to the half wave cavity. So it's difference between the length. If you look at the pros and cons between the two, for a given frequency, preferably very low frequencies, the half wave cavity requires 50% less structure compared to the quarter wave cavity. It requires 50% less structure compared to a half wave cavity. And you gain more power out of the half wave cavity compared to the quarter wave cavity, and so on. But as I mentioned, at some point, even though these factors are true in terms of power and size, because of this vertical electric field that's here, the quarter wave cavities cannot be used for betas much higher than 0.2 around. And also for the quarter wave cavity, because of this inner conductor is only mounted at here, it's not mechanically stable to go at much larger cavities as well. So And then quickly going on to the spoke cavities. So if you notice, the single spoke cavity is it's very similar to half wave cavity, only that the cylinder is rotated in a different orientation. But then this allows you to do multiple gaps easily, because you can put a cylinder in this way and you can have more spokes, which is rotated by 90 degrees between each spoke, and you can have a higher effective voltage across the gaps, and with very strong cell-to-cell coupling. So that's the advantage of going into spoke cavities compared to using many half-wave cavities. So as I said, the half-wave cavity and single spoke cavities, the dimension-wise, it's the same. Only difference is that the cylinder is rotated in a different orientation. So the preferable cavity choice is half-wave cavities are very much good in very low betas, and usually around 150, between 100 to 100 megahertz, where the spoke cavities you can go above higher frequencies, 300 to even 500. Beyond that, it's quite large to manage. Even 325, it's quite large, but you don't want to do spoke cavities at these frequencies at all. But then for higher betas, the preferable ones is spoke cavities. And I showed you earlier that we have done high beta spoke cavities operating at 0.8 and 0.1 beta. So this is the two cavities that I showed. This is a 325 megahertz 0.82 beta cavity. It's almost more than half a meter diameter, so you can understand the scale of it. And this is in the lengthwise, this is closer to a meter. But these are very good for small compact light sources or small machines where you want you can have the 4K operation. And at 4K operation, these have high mechanical stability, and you can design those cavities to have high shunt impedances, so you have much smaller power losses. So you have the freedom to optimize these cavities to suit the application. So there are several cavity applications that I have put down based on the frequency range and betas. Because of the limited time, I'm not going to go through them, but you're welcome to have a look at them. And so this is the twin axis cavity that I talked about, where you have a TM110 type with electric field in the two beam pipes to separate multiple beams at the same time. So this one was proposed for energy recovery linacs, and you can use it for where you have the merging of the two beams in an energy recovery linac, or even to accelerate one beam and decelerate the other beam. So you use the energy of the decelerate beam to accelerate the other beam. So you can use the power efficiently. But this is a prototype build. It's not used in a machine at the moment, but there's potential in the cavity geometry. So let's quickly go on to the deflecting and crabbing cavities. As I explained, the cavity geometry doesn't change based on whether it's a deflecting cavity or crabbing cavity. It all depends on the RF phase in which the voltage is applied to the particle. So if you apply the voltage at the center of the bunch, like shown here, what it does is the whole bunch get deflected. So that's what we call a deflecting cavity, where the whole bunch is deflected. What you need is a transverse electric field to kick the whole bunch. Then the crabbing concept is used mostly in particle colliders. It can be circular colliders or even linear colliders, such as ILC. What you do is you want the two bunches to be colliding head-on instead of coming at an angle, instead of colliding at an angle, because the bunches come at an angle which is called the crossing angle. So you want to align them to collide head on, and what you do is you kick the head and tail of the bunches in opposite direction, and you started rotating the bunch such that by the time it comes to the interaction point, they are aligning well. So you can have maximum number of collisions between the two bunches to increase the luminosity. So so these cavities can be either transverse electric field, or you can even use magnetic field, or both of them. So similar to what we saw in the accelerating cavity, you simply integrate the fields, but now in addition to the electric field, you have a magnetic field, and these are all transverse fields, not electrical fields. So based on the field geometry, it can be a TM type design, and where the contribution is coming from a transverse magnetic field, and it can be either TE, where it's a transverse electric field, or a TEM type with both transverse electric and magnetic field as the contribution. So I put down here two current applications that's implementing these cavities. One is the LHC high luminosity upgrade, where they will be installing two crabbing systems or several crabbing systems at two interaction points, which are the Atlas and CMS. The other current application which just started into project level is electron ion collider. Here there's proposed two interaction regions, one here and one here, and this is the collision between electrons and protons. In the LHC, it's a collision between proton and protons. Here you have actually a very large crossing angle, and you need, because of this large crossing angle, you need two frequencies for the proton ring to crab, and these are the 197 megahertz and 394 megahertz. And this is a 197 megahertz RF dipole style crab cavity, and then for the electron ring, it's only 394 megahertz. So looking at the field profile, I said these cavities can be TM, TE, or TEM. So first, let's look at the TM type. And here, the contribution to the deflection is coming from this transverse magnetic field. So you have the magnetic field coming out of the plane, and with the V cross B, it gives a kick in the transverse direction so that you can use it as a deflecting or a crabbing. The advantages of this one is you have these cavities are not favorable for very low frequency because of the size, because the dimensions are inversely proportional. So when you go to low frequency, these cavities are quite large, and so they are mostly preferable at high frequency. One of the advantages, since we are doing TM110, you have the TN010 mode before this mode, which is a lower order mode. So you have to damp that mode too. So you need a notch filter also to damp the lower order mode. And here are two cavity examples. The first ever deflecting, superconducting deflecting cavity that was built is A, operating at TM110. It's a mini multi-cell cavity. Now it's not in commission. And the first ever crabbing cavity, which is also a TM110 cavity, that was built at Japan for the Super Big Factory. And you can see the dimension. This cavity is half a gigahertz or 500 megahertz. And the width itself is half a meter and almost a meter tall. So you can see the cavity size compared to a person, how big this cavity is. So it operated successfully between 2007 to 2010, but it's no longer in operation. And then another type is a TEM, where you have a transverse electric field and you use a magnetic field both to create the net deflection. The advantages of these is you can use these for very low frequencies. At low frequencies, these are ideal for compact designs. and you do not have low order modes. So, so these cavities are used in, I mean, not used in a machine at the moment as a crabbing cavity, but this is the normal conducting TEM type cavity, which is a copper cavity used as a deflecting cavity at JLab at 500 megahertz. They also have a 750 megahertz cavity that's currently used in the machine. There was another superconducting version designed for LHC, 400 megahertz cavity. It also performed well when it was prototyped, but it's not implemented in a machine. The other ones are the TE one, where you use a transverse electric field, no contribution to the magnetic field, but uses primarily the transverse electric field to create the net deflection. So two of these cavities are the double quarter wave cavity and the RF dipole cavity. And these are the two cavities that's used in the LHC, and they are both in production now to be included in the LHC for the high luminosity upgrade. So you can see the transverse electric field. This cavity is used for vertical crabbing. This is the double quarter wave where you have the strong electric field between the two gap, And this is the crab cavity used for horizontal crabbing. This is the transverse electric field you can see here. There's also multi-cell cavities. There was a prototype cavity that was designed for J-like. It's in work in progress to complete fabrication and testing. Another high frequency multi-cell TE cavities, which is called the Comunidad cavity. And it's a very high frequency, and this is the size of the beam pipe. So you can imagine how small this is. But it also performed quite well and in the cold test. So I quite rushed through at the last slides, but however, what I wanted to show was give an idea of different types of cavities out there in this interesting field with all these non-elliptical shapes. The work in this field has been going on for several decades, like for the past 40 years. And they are being proposed for many applications, and they are highly effective in those applications. Recently, they have been included them for machines such as the FRAVE, ESS, and then the LHC and EIC for deflecting, basically crabbing cavities. They're also proposing it for ILC for crab cavity. That's in work in progress. But the hard work that's been put up by all these people have made this field evolve similar to the EIC cavities and to address many other key issues related to this field that has not been seen in the elliptical cavity regime. So you guys are welcome to explore this field and think big and come up with more innovative cavities. Thank you.
Thanks, Suba. Thank you very much. So if anybody has a question, please, anything that you, there you go, Pavel, go ahead.
Cheers. Thank you very much for this very nice presentation. It was very well elaborated, very nice work. I just have a question regarding how do you calculate your electric fields? Which of those programs that you show is the one that you normally use?
I use CST. That's the one that I have been used, and actually that's the most common commercially available code that you can use to simulate those. And it's over the years, it has got better and better, has advanced, and they have included many things related to cavities that you can use in these in calculating different cavity properties. I also use the Slack S3P code. it's not user friendly, but it's a highly effective code as well. And then similar to CST is the HFSS. HFSS is combined to ANSYS. So if you do it in HFSS, you can easily convert these electromagnetic design into study the mechanical side, the structural and thermal and so on in ANSYS. So I would say all these codes are well advanced and you can use them readily, easily. Some are user friendly, but some are not. But I think once you kind of get used to a certain code, you can catch up on a different code pretty easily.
Thank you very much.
Okay, well, thanks, Pavel. Thanks, Suba. Bruce, you have a question?
Yes, thank you very much for the presentation. I have a comment. I want to hear your opinion about which are the main challenge for, let's say, for this no elliptical cavity. I mean, usually elliptical cavity has, let's say, a lower E-peak ratio. I mean, magnetic or electric one. However, for let's say for HWR or Spock, the peaks are a little more higher. Can you have any comment about that?
Yes, yes, that's true. But so you may not be able to compare it exactly like that because the elliptical cavity is in a different regime at a beta equals 1, right? And then if you use the same beta that you define or design the half wave or the spoke, these E peak field or B peak field ratios are not going to be good in elliptical cavities, right? So so at low beta, you still get good performance out of those these type of cavities than you can get out of simple elliptical cavity. One area you can compare is the high beta region. The high beta region, you have elliptical cavities as well as spoke cavities. And the spoke cavities in high beta, say 0.8 or 1, you have slightly high peak field ratios compared to a standard elliptical cavity. But there are other advantages where you can use this kind of cavity. So as I said, at very high beta, you would not want to use spoke cavities for particle acceleration for a big machine like ESS or even FRIG. For those, you want to go to elliptical cavities because of the simplicity of the geometry in fabrication and as you said, peak fields and so on. But if you want to design a compact machine where you need only maybe one cavity or two cavity at most for a compact machine, then and then say that you don't even have 2K helium available. What you have is because you may not have a refrigeration, but you still can have 4K. Then mechanical wise, the stability is much higher in these high beta spoke cavities compared to the elliptical cavities. So even if it's for simple electrons, then you would want to go to these kind of spoke cavities, and you can optimize them not based on the peak surface fields, but based on the shunt impedance, because since you're using 4K and running only like 1 or 2 cavities, you try to reduce the power loss. And then you do compromise a little bit on the peak fields, but then you are not trying to accelerate particles to maybe giga electron volts or even high energy. It's maybe like 10, 12 or 15 to 20 MeV you are talking about. So you can compromise the peak fields, but get good shunt impedance. So yes, as you said, I would not go on doing these complicated cavities at high beta regime for bigger machines. But yes, they are much, much better compared to elliptical cavities for small machines.
Just a little bit, an extra comment. When you mentioned about the advantage and disadvantage, I mean, when you put that, when you, let's say, go to low beta for elliptical one, you start to see that there is not so much stability, and also you have this issue about the multipathing that you can achieve. However, for instance, in a spoke cavity also, because I mean, the part of the cavity also could be quite near, and also the problem of the multipathing can also occur for the geometry itself. So I mean, I think that it's important to say there are advantages and disadvantages.
Yes.
So using that.
Yes, very true. So spoke cavities are famous for hard multipathing. But you can process them, take much longer and longer to process them and clean them. So in regarding to spoke cavities, you do see multipathing barriers, but over the time of processing, you can clean them. But the multipathing that I was referring to in the very low beta elliptical cavities are in the equator, where you have trapped resonances. And those are not easy to clean. They are very hard barriers and actually make it impossible for the cavity to be processed. So the multipathing in the spoke cavities, yes, it's severe than standard elliptical cavities at beta 1 you see, and you need more processing time, but you can process it and clean it. And one advantage of spoke cavity is because of these multiple parameters that you have, you can optimize the shape by curving differently these edges without having any impact in the spoke gap, and optimize the geometry and not compromise the performance and still reduce multipathing. But with the limited parameters in the elliptical cavities, you don't have much freedom, right? Because of the elliptical shape, you have only like a handful of fewer parameters. And at very low beta, these parameters does not support you in optimizing the shape well to eliminate multipathing. And then you may live with very hard barriers that's hard to process and can be quite detrimental, that you really cannot have a cavity at that particular frequency and beta.
Okay, thank you very much.
Anybody else has any other burning question? Otherwise, we thank again Silva for the nice talk. There you go. Juan has a question, so we hold on the thanks. Go ahead, Juan.
Yes, hello. Thank you, Dr. Silva, for your nice presentation. So I have a very simple question, probably it's quite naive, but I was wondering about the advantages of using these non-elliptical cavities to deflect the beams compared with using, I don't know, a simple bending like a magnetic dipole or something.
Magnet. Yes, that's true. There are cases that you can get away with a magnet, but if you want to deflect the beam at a very fast rate, then the magnets are not effective. So that's a different study. Based on your application, you want to do a study and see whether you can, it's something at a rate you can do with just a simple magnet. Or if it's a very fast rate, then you don't have an option and you have to go to cavity. Yes, so that based on the application, you have to do that first before you jump onto a cavity, start doing a cavity design.
Okay, thank you.
Thanks, Juan. So anybody else want to jump in? No? Okay. Then thanks again to Silva. for the talk and everybody else for logging in and to this nice seminar. So we hope to see you in the next one. And as Suba said, for example, we have the proposal of having a basic RF cavities seminar. So if anybody's interested in preparing this, they are more than welcome. So,
Alex, can you allow me to make a brief announcement? And basically, in 1 month, February, April the 9th, we want to have another seminar for Kathleen from CERN, who will give us a talk. So please see you in 1 month, more or less.
Excellent. Thanks, Bruce. So see you, everybody. See you, Suba. Thanks again.
Thank you. Bye, Sal. Take care.
See you, everyone.
Thank you,
Have a nice
Suba,
weekend.
for your time and for giving this
No
talk
problem.
to us.
Thank you. Bye-bye.
Bye.
Cheers.